What's up, everyone? This is the Round Bottom Flask, and welcome to the part 3 of our video lecture series for the colligative properties of solutions. So in this video, I will be talking about osmosis. So let's have some sort of a theoretical experiment here. So let's say we have two sugar solutions of different concentrations and are in the same container but separated lang sila with a semi-permeable membrane. So what do you mean when we say a semi-permeable membrane? It is some sort of a barrier or a thin membrane which has pores only large enough for some molecules to pass through. Okay, in this case, only the water molecules, which is the solvent here in the solution, is only small enough for it to pass through the semi-permeable membrane. Now, ang solution sa left side ng semi-permeable membrane is the one with a low sugar concentration, kag ang sa right side ng semi-permeable membrane is the solution with high sugar concentration. Now, if you can see here, these two solutions are in contact with each other via the semi-permeable membrane, and there is what we call a concentration difference on both sides of the semi-permeable membrane, or a concentration gradient. Now, usually when there is a concentration gradient, for example, you mix two solutions of varying concentrations, what happens there at the molecular level is both the solute and the solvent molecules will diffuse themselves all over the bulk of the resulting solution pag mix mo sa ilang duha ka solutions nga of the different concentrations. Now, it also similar to this, like dumping two solutions of different concentrations in the same container. Galing, there is a semi-permeable membrane. So, since the sugar molecules are too large for it to pass through the semi-permeable membrane, hindi siya maka-diffuse all around the bulk of the solution para madula ining ginatawag nga concentration gradient. So what happens here is that only the water molecules will move. Okay, now since this has a lower concentration of your solute, of your sugar or your solute, and this side here has a higher sugar concentration, what will happen here is water will move to to the solution of higher concentration para mag-dilute ni siya. Kag ang lower sugar concentration, mas mangin concentrated siya until nga magparihas ni ang concentration on some solutions on both sides of the membrane. And that phenomenon, or that net movement of your water molecules or solvent molecules, is what we call as osmosis. So remember that in osmosis, the movement of your solvent molecules will be from a lower concentration of solute to a higher concentration of solute, and will only stop once that concentration gradient has been addressed. So let's have another osmosis experiment similar to this one, but instead of placing this, let's say this is a beaker, let's place it in a U-shaped glass tube. Okay, the same with this one. So left side is a lower concentration of solute, kag sa right side has the higher concentration of solute. So by virtue of osmosis, the movement will be from the left side. The movement of your solvent molecules or water molecules will be from the left side to the right side. Now, since ibang nga water molecules mo mabuhinan diri nga side, kag diri nga side madugangan, so obviously the volume of this solution at the right will increase while the volume of this solution at the left will decrease. So there will be, so the level of this solution will rise and the level of this solution at the left side of the semi-permeable membrane will lower until until the concentrations of both sides of the semi-permeable membrane will decrease, will be the same. Now, let's say you want to bring it back to the initial state. So what you will do is you will apply an external pressure here on the solution with a higher level, so that you will push the water molecules that has previously diffused from the left side to the right side, and you will make it return to the left side of the membrane, wherein the lower solute concentration was initially located. So you will revert it back to the original state, such that nga mabalik si lower concentration, mabalik ang original nga concentration gradient. So you can do that again by applying an external pressure, which is against the direction of the solvent movement. So since ang solvent movement mo is going here, going to the right side, so your pressure, your application of your external pressure should be on the left, okay? Now, that minimum pressure required to stop osmosis is what we call as osmotic pressure. And osmotic pressure, just like your vapor pressure, your boiling point, and your melting point, is also a colligative property of a solution. So this is the formula for your osmotic pressure, wherein I will be obviously our Van 't Hoff factor, and M will be the molarity of your solution in moles per liter, and R will be your gas constant, which is the one used in solving ideal gases and in the ideal gas equation, and the temperature in Kelvin. So your osmotic pressure is expressed in atmospheres. Okay. Now, because of the presence of this osmotic pressure, you can actually or rather, your solutions are can be classified in terms of their relative osmotic pressures with respect to their external environment. If the reference solution is isolated by a semi-permeable membrane. So let's have the first category is your isotonic or isosmotic solution. So an isotonic or isosmotic solution will have an osmotic pressure equal to the osmotic pressure of the solution on the other side of the semi-permeable membrane. So that means the osmotic pressure on both sides of the membrane is equal. That means, since osmotic pressure is a colligative property, both solutions on either side of the semi-permeable membrane has equal concentration. So let's have a biological example, which is a red blood cell. Now, a red blood cell is, the membrane of a red blood cell is semi-permeable, which only allows water molecules to pass through it. Now, if the red blood cell is isotonic with respect to the external environment, there will be no net movement. There will be no net movement of your water molecule. So that means water go in the red blood cell the same rate as the water that going out the red blood cell. Next is we have a hypotonic or hyposmotic pressure, wherein the osmotic pressure is higher than the other side of your solution. So what does that mean? That means that in a hypotonic or hyposmotic solution, the concentration of your reference solution is lower than the concentration of the solution on the other side of the semi-permeable membrane. So, because lower ang solute concentration sang imong reference solution sa pihaka side sang semi-permeable membrane, in order to address this concentration gradient, your solvent will move out from that hypotonic solution. So let's have an example of your red blood cell. So the insides of a red blood cell has a lower solute concentration, while the outsides of a red blood cell will have a higher solute concentration. So what will happen is that in order to address the concentration gradient, so water molecules inside the red blood cell will move out of the red blood cell so that mag-equal ang concentration on both the inside and outside of the red blood cell. So as a result, your red blood cell will shrink or will wrinkle. Lastly, we have a hypotonic solution or hyposmotic solution. Now, in a hyposmotic solution, its osmotic pressure is lower than the other side of the semi-permeable membrane. That is, its concentration is higher than that of the solution on the opposite side of the semi-permeable membrane. As a result, in order to address that concentration gradient, the hypertonic solution will be diluted by taking in solvent molecules. So going back to our example, select red blood cell. Now, in a red blood cell, if the outside of the red blood cell has a lower solute concentration compared to relative to its insides, so water molecules will pass through the cell membrane and will move into the red blood cell in order to address this concentration gradient. And as a result, your red blood cell will swell. And if the concentration gradient is really great, such that the osmotic pressure is too high, what will happen is, worst case scenarios, your red blood cell will burst. Okay. In this next portion, I will be showing you some quantitative problems regarding osmotic pressure and on how to solve them. Here's our first example. Biochemists have discovered more than 400 mutant variants of hemoglobin, the blood protein that binds oxygen and carries it to the body cells. A physician dissolves 21.5 milligrams of one variety in water to make 1.50 milliliters of solution of 5 degrees centigrade. She measures an osmotic pressure of 3.621 torr. What is the molar mass of the protein? So before anything else, we need to write our given so that we can determine what figures in the problem is needed to what is needed to solve the problem and get you to the correct answer. And also, we can also it will also help us identify what important figures or constants have we missed out, which are not stated in the problem, but we need this to solve to arrive in the correct answer, to the correct answer. So we have your 21.5 milligrams of your hemoglobin. We abbreviate it as HB. Then our volume, which is equal to 1.50 milliliters. The temperature of your solution, which is equal to 5.0 degrees centigrade. And we know, since in calculating the osmotic pressure of your solution, your temperature is expressed or should be expressed in Kelvin. So we can convert this directly to Kelvin by adding it to with a value of 273.15. So that is equal to 278.15 Kelvin. Next, we have the osmotic pressure, which is equal to 3.61 torr, and we still need our what they call this, our gas constant, which is 0.08206 liter atmosphere per mole Kelvin. So you should be familiar with the universal gas constant by now, because you will be using it most of the time, a lot of times in general chemistry. So then we write what is needed. So we need the molar mass of your hemoglobin. So then we got to the solution. So let's go back to the formula for the osmotic pressure, which is equal to I mRT. Now, since hemoglobin is a protein and thus a biomolecule, it is assumed that its Van Hoff factor, or it is assumed that it is a non-electrolyte solution, or a non-electrolyte, thus its Van Hoff factor is equal to 1. Okay? And we also know that molarity is the number of moles of your solute divided by the volume of the solution. So we can substitute this expression to our formula for the osmotic pressure here. So it would look like this, substituting this expression of molarity to your first equation would make it look like this. So I n over v multiplied by RT. Okay. Now we already have the osmotic pressure, the volume of the solution, which is 2.15 mils or 1.15 mils. Then we have our gas constant, and we also have our temperature. So we don't know this one. And we know that in order to determine the molar mass of your hemoglobin, we need to know how many number of moles of hemoglobin were used in this experiment or in this problem. So we rearrange the equation such that only the n, or the number of moles, is on one side of the equation. Therefore, n is equals to pi over v over I RT. So then we substitute the value. So we have 3.61 torr. However, since the pressure is in atmosphere, so we need to convert this to atmosphere. So we know that 1 atmosphere is equal to 760 torr. So this will be our conversion factor to convert this to atmospheres. So obviously our unknown value, which is unknown unit, is atmosphere. So it will be in the numerator portion of your conversion factor. Then at the denominator will be your torr, which is 760. Next is we multiply this with our volume, which is 1.50 milliliters. And since our volume should be in liters, we need to convert this to liters. So our conversion factor is 1 liter of your solution is equal to 1,000 milliliters. Next is we divide this with our universal gas constant, liter atmosphere per mole Kelvin multiplied by our temperature, which is how much is that? Wait, then, sorry, which is 278.15 Kelvin. Now, guys, this is a 7. Oops. Okay. So this will cancel out. This will cancel out. This will also cancel out here. And this one and the liters here. Okay. So solving this, the number of moles that you have is equal to 3.1215787 times 10 to the negative 7 mole. Okay, so that is the number of moles of hemoglobin that was used in the experiment. So we need to get the molar mass of your hemoglobin. So we know that the molar mass is equals to the mass of your substance in grams divided by the number of moles of your substance, which is number of moles. So then we divide the mass of your hemoglobin into the number of moles that we have already solved from our osmotic pressure data. So we have 21.5 milligrams of your hemoglobin, and we know that your molar mass is grams per mole. So convert this first to grams, which using the conversion factor from milligram to gram. So 1 gram is equal to 1,000 milligrams. Then we divide this with the number of moles. So notice that I placed so many decimal places here, or decimal figures here. I did that because this is not yet our final answer, and we want to minimize or to mitigate errors due to rounding off. So place as many decimal places as you think is necessary, so that there won't be any significant errors due to rounding off of your decimal places. So we have 3.1215787 times 10 to negative 7 mole your hemoglobin. So, and your answer is rounded, since it is quite a large value, so we'll just round it off to the nearest whole number. So the answer is, to the nearest whole number is 68,000. 68,875 grams per mole. So that is the molar mass of the hemoglobin variant used in this experiment. So let's have another example. What mass of sucrose with this given chemical formula would you combine with 500 grams of water to make a solution with an osmotic pressure of 8.55 atmospheres at 298 Kelvin? Assume a density of 1.0 grams per ml for the solution. So in this case here, it was assumed that the density of your solution is the same as the density of your solvent, which is water, since the density of your water, the density of water is also 1.0 grams per milliliters, and we will use that assumption in order for us to easily solve this problem. So again, we'll write our given. So we have density of your solution, which is equal to 1.0 gram per ml, and this is also equal to the density of your water, and we're given 500 grams of your water the osmotic pressure of your solution is 8.55 atmospheres, and the temperature is 298 Kelvin. So what is required is the mass of your sucrose in grams. So let's say we abbreviate sucrose as SUC or SC. So then solution, sorry about my really messy handwriting, guys. So first thing is, so what we should do is we get first the molar concentration of your sugar solution in terms based on the osmotic pressure data. So we'll use the formula for osmotic pressure. Pi is equals to I mRT. And we know since sucrose is a non-electrolyte, it is assumed that its vapor pressure or its Van 't Hoff factor is equal to 1. Next, then we rearrange this equation so that only the molar concentration, which is M, will be on one side of the equation. So we divide both sides of the equation by I RT. So this will be cancelled out in the right side. Therefore, M is equals to pi over I RT. Next is we substitute our values. So we place 8.55 atmospheres here. So again, I will not place the Van 't Hoff factor, the value for the Van 't Hoff factor in our, or I will not substitute the value for the Van 't Hoff factor in this equation here, since it is the Van 't Hoff factor is 1 and any number multiplied or divided by 1 it is the number itself, so there will be no change in the values. So I will write directly the gas constant, which is 0.08206 liter atmosphere per mole Kelvin multiplied by the temperature, which is 298 Kelvin. So cancel out all your necessary values. So the molar concentration is 0.349638. Sorry, I have already solved the problem beforehand, so that's why I'm not looking. That's why I'm not looking direct. At times I'm not looking directly on the screen. So 0.349638 molar, or can be also expressed in moles per liter. Now, since we have since the density of the solution is equal to the density of water, it is also therefore safe to assume that the volume of the solution is equal to the volume of the water used in preparing the said solution. So therefore, we need to convert this 500 grams of water to milliliters using its density. Since the density is 1 gram per ml, therefore 500 grams of your water is also equal to 500 milliliters of water, and that is also the volume of your solution, which is 500 milliliters. So we use that to we use that and the molarity of your solution to get the grams of your sucrose that is needed in this problem. So we have 0.349638, or rather, let's write first the volume of the solution, which is 500 ml. So 500 ml, we convert this to liters using the conversion factoring of 1 liter is equals to 1000 milliliters. So that will cancel out. Then we will use molarity as some sort of a conversion factor in order to get the number of moles present in the 500 ml of your solution. So since we need to cancel out the liters to get to them, and only the mole, the unit mole will remain, so the liter will be at the denominator of the said second conversion factor. So it will be 1 liter, and the moles will be this one here at the numerator. So it will be 0.349638 mole of your sucrose per 1 liter of your solution. So that will cancel out. Then, since we will get the mole from this expression, we will now use the molar mass of your sucrose to get the mass of the sucrose that will be needed to prepare this solution. So we will use, so I have already calculated the molar mass of your sucrose, which is 342.296 grams of your sucrose over 1 mole of your per 1 mole of your sucrose. So that will cancel out as well. And the answer is, rounded off to 4 significant figures, is 59.90 it's 59.84 grams of your sucrose. So let's have our last example here. A 0.86% by mass solution of sodium chloride is called physiological saline because its osmotic pressure is equal to that of the solution in blood cells. Calculate the osmotic pressure of this solution at normal body temperature, which is at 37 degrees centigrade, and this solution has a density of 1.005 grams per milliliter. So let's write first our given. So we have a 0.86% weight per weight or mass per mass of our sodium chloride. Then we have our temperature, which is equal to 37 degrees centigrade. We can convert this again to Kelvin by adding a value of 273.15, and that is equal to 310.15 Kelvin. The density of the solution is 1.005 grams per milliliter. And we know that since sodium chloride is a strong electrolyte, so this dissociates into its respective ions in solution, which is sodium, cation, your chloride anion, so it will produce 2 ions. Therefore, the Van 't Hoff factor of your sodium chloride solution is 2, or the theoretical Van 't Hoff factor is 2, and the universal gas constant, which is 0.08206 liter atmosphere per mole Kelvin. So what we're looking for is what is required in this problem is the vapor or the osmotic pressure of the said solution. So how do we solve this one? So since we're given percent mass of your the concentration of your solution in percent mass, we assume 100 grams of your solution. So since we have 100 grams of your solution, it is also assumed that it will contain 0.86 grams. So that is why we use an assumption of 100 grams, because we know that since this is in percentage, 100 grams of something is equals to that percentage of that entity. So since we have 100 grams of your solution, that means it contains 0.86 grams of your sodium chloride. And we know that the osmotic pressure is equals to IMRT. Okay? So we already have this one. This is a constant, and this is and it is also given in the problem, but we do not have the molarity of your solution. So how do we solve for the molarity of the solution? We solve that from this assumption and using also the density of your solution. So we know that the molarity is equals to the moles of your solute, which is sodium chloride, divided by the volume of your solution in liter. So how do we get the volume of your solution? We use the density of your solution and from our assumption of 100 grams. So we have 100 grams of your solution. We use the density as a conversion factor. So we have 1.005 grams of your solution as the denominator in the conversion factor, and the numerator is your 1 ml of your solution. And that is equal to 99.50249 milliliters of your solution. So we already have this one. We can now use this to get the molarity of your solution. So your molarity is equal to moles of your sodium chloride, which can be obtained from this amount of your sodium chloride present in 100 milliliters of your 100 grams of your solution, and we convert this to mole using its molar mass. So 0.86 grams of your sodium chloride. We convert this to moles by using its molar mass. So we have 1 mole of your sodium chloride divided by 58.44 grams of your sodium chloride. Next is we divide this with the volume in liters. Since this is in milliliters, we convert this to liters. So in the denominator, it will be 99.50249 milliliters divided by, converted to liters using its conversion factor, 1000 ml, 1 liter. So the molarity of the said solution is equal to 0.1478953 mole per liter. Thus we can now solve for the osmotic pressure of your solution. So we already have now the molarity. All we need is to plug in our values. So osmotic pressure is equal to 2, which is our Van 't Hoff factor, multiplied by 0.1478953 mole per liter, multiplied by the gas constant, which is 0.08206 mole liter, liter atmosphere rather, liter atmosphere per mole Kelvin multiplied by the temperature, which is 310.15 Kelvin. Cancel. Cancel. So this will also cancel out. Thus, the osmotic pressure is equal to, rounded off to 4 significant figures, 7.528 atmosphere. So this is the end of my video. I hope you've learned something from it. And if you have further questions regarding this topic, or let's say you have suggestions on what chemistry topic should I cover next, please feel free to drop it in the comment section below this video. And if you like this video, please don't forget to click the like button and subscribe to my YouTube channel for more chemistry related lectures. Again, this is the Round Bottom Flask signing off. See you guys.